Hello all, and welcome to this next session of the course Pre-MBA Statistics. Now the topic that you see in front of you is kind of really practical, and then a lot of people sort of apply this idea about regression. So I'm very sure that many of you might have heard about this term regression, or rather regression analysis, or linear model fitting, and so on and so forth. So this is exactly what we'll spend time on in the subsequent sessions in this week. So now we're entering a new week, which is the last week of this course. And we have discussed all this while about, let's say, testing of hypotheses, then random variables, different distributions, confidence intervals, estimation, etc., etc. Now let's see that how do you sort of combine all the ideas of, let's say, be it a normal distribution, parameter estimation, etc., and sort of try to build upon a predictive model to sort of predict a output. Okay, so this entire idea about regression is more in line with doing some prediction now. So ultimately, let's say if you understand the data set, if you understand the underlying distribution, statistical properties of the data, etc., and let's say down the line if you want to predict something or forecast something, then how would you make use of a model per se, which is called as a regression model, to sort of answer the questions that you have. Okay, and again I have put regression and beyond. So again the first session will be kind of very basic, where we'll discuss some definitions. I'll go through several examples. I'll try to explain what exactly is the regression model we're talking about, what exactly are the underlying parameters in the regression model, and so on and so forth. Okay. Alright, so we'll start with again very basic, like I said. So regression analysis, where exactly can you use it? Okay, so we'll try to answer that very quickly, and subsequently we'll see a number of different examples coming from different areas. Okay. So regression analysis helps us to answer many practical questions. So again, like I said, regression, this entire idea about modeling per se, or regression modeling, regression model fitting, right? It sort of is more practical, or rather kind of a practical idea to sort of begin with and try to analyze the data that you have. Okay. Now again, what sort of questions regression analysis helps us to answer, we'll see subsequently. So we'll start with a couple of examples. The first one is, let's say, what's reducing the life expectancy in the US. So in front of you, you see a nice little curve, and let's say over a number of years, so it's kind of a time series data. So again, in this session we'll not spend time on time series data, but again per se any data set which depends on time. So let's say you're collecting some yearly observations or daily data, monthly data, let's say sales data which you're recording every day or every week, etc., are called as time series data. So again here you have a time series data, because on the x-axis what you have are nothing but years. So all the way from, let's say, 1990 to 2015, and then you have a chart in front of you which shows you the life expectancy and its behavior. Okay, so let's say initially in the year 1990 the life expectancy was kind of low, around 75, but down the line it sort of increased to 78.8 in the year 2015. Okay, so a couple of very easy conclusions one can make out is that this line shows some trend, right? Now again, what you mean by trend is nothing but some upward movement or downward movement of the behavior of the data set. And again, like I said, trend means nothing but certain ups and downs which you see in the data set inbuilt. Okay. So now the idea behind regression is to sort of fixate on a particular model which is more like a linear model. So again, we'll spend some time on understanding this idea very soon. But the moment we talk about regression, at least for this course, we'll stick only to linear models. Okay, and the moment I say linear models are nothing different from an equation of a straight line. So now things are, or other things should fall in place for all of you, that you must have studied the equation of a straight line back in school or back in college days in your maths course. Okay, so the exact same idea we'll try to borrow here. And again, what exactly is the difference from an equation of a straight line to, let's say, a linear model, and then how would you use a regression model to sort of forecast or predict down the line? That would be the important part. Okay, but again, just to reiterate that we'll spend time entirely on sort of developing a linear model and not a non-linear model. And linear model means what? So let's say if you see this graph in front of you, I have to somehow fit a straight line which sort of describes the behavior of that curve. Okay, something like the red line which I just drew. Okay, And the whole idea of developing this regression model, or let's say a regression analysis, is to sort of put forward an equation or a model of that red line, which is nothing but a straight line, which describes the data to the maximum. Okay. Alright, so this is a broad idea about regression modeling, and then we will see what are the nuances, then how do you construct that model. You require some assumptions inbuilt in the model. We will discuss all those things subsequently. Okay. Now again, just to understand, we are starting with very basic examples. The first one, like I said, is life expectancy from 1990 to 2015, and then you can clearly see the upward trend and then the general ups and downs in the data and so on and so forth. Slightly different example. So you see a map of the US in front of you, and you see number of different colors. So some states are in red, some states are in blue, etc., etc. But what do all these colors measure? Okay. So the problem in hand is to sort of understand that how much of cancer mortality rates are related to where a person lives within the US. Okay. So couple of things. So how many variables do you see here in the statement of the problem? Precisely two. So the first important variable is cancer mortality rate, and the second important variable is nothing but the location of that person. So related to where a person lives, so you can sort of pinpoint to, let's say, a longitude and a latitude, or nothing but the coordinates of that person, and those coordinates would be another variable. Okay. So again, to break this problem down, it's sort of asking that if you change the coordinates of a person, how do the coordinates of a person affect the cancer mortality rate? Okay. And again, like I said, if you see, so slightly not very easy to sort of visualize this, but different colors have different mortality rates basically. So the states in the red have higher cancer mortality rates down here on the west side or on the northeast portion of the US or in the north, and especially if you move south, then the cancer mortality rates reduce. Okay. So essentially, can you sort of try to formulate the problem in your minds now? So if a person moves from north to south, what should happen to the cancer mortality rate? So from this data, we can understand that as a person moves from north to south, especially if you talk about US only, then the cancer mortality rates reduce. Okay. So the cancer mortality rates also reduce if you are moving from north to south, from let's say some state in the north to let's say some state in the south, for example Texas or Alabama, etc. Okay. And by the way, this is a slightly old data. So and then this focuses only on, let's say, white females, and over the years 1970 to 1994. Okay. So let's try to understand that what exactly is the problem here, and then how could the problem be solved using regression analysis or a regression model. So I think that's the more important idea to sort of understand here, that once you establish a regression model, how do you sort of make use of the regression model to sort of understand the behavior in the data set, or the more important aspect is to sort of form a link between where a person lives to nothing but the important variable, which is cancer mortality rates there. Okay. Alright, so one more very easy example. So you see number of students sitting and then giving some exam, preparing for some exam, and now the problem in hand is that how well do college percentages predict CAT scores? Okay. So again, two variables here. On one hand, we have college percentage scores, and then you want to predict the CAT scores based on the college percentage scores. Okay. So again, if you sort of form a link here, the link, or rather the arrow should be in that direction. So you're using the college percentage scores to predict the CAT scores of the examinees. Okay. So we've seen three examples up till now, and then in every example now you'll have a sense that if you want to create that regression model, there should be two very important variables in hand. So x and y. Okay. And what exactly is the variable x, what exactly is the variable y, we'll sort of define them formally very soon. But for example, if you focus on this example that's there in front of you, then y could be nothing but CAT scores, and then x could be nothing but college percentage scores. Okay. So and then the idea about regression model is to form a linkage between x and y, or rather using x, how do you, or rather how can you predict y? Okay. So again, the arrow is in that direction. So taking the information from x and y subsequently, but then taking information from x and then using that to predict information about y. So this is the whole idea about regression analysis. So even these days you've been hearing things about, let's say, machine learning or deep learning and so on and so forth. But again, the crux of all these hi-fi sort of, or not exactly hi-fi, but the slightly advanced models is nothing but regression. Okay, so regression is nothing but a starting point of many more advanced machine learning techniques or deep learning techniques, etc. Okay, so again, of course, we'll not have time here to sort of spend on machine learning per se, but then if you understand regression, then almost, let's say, 80% of the problems could be fitted using a regression line. I mean, this is exactly what people in the industry do these days. Okay, so they try to fit, let's say, if not a linear regression, but let's say non-linear regression and so on and so forth, but some sort of a regression model you can sort of try to fit on the data set that you have. Okay, and for fitting the regression model, what are the ingredients you require? You only require two variables at least. So one y and then one x or several x's there. Okay. And for example, this is exactly what we'll see in the last example now. So the problem in hand is factors affecting BMI, and then you have several factors, so age, gender, exercise, etc., etc. Now again, here this example is slightly different from all the earlier three examples you've seen, and again, in what sense? So again, you may pause the video and try to answer this question, that how exactly is this particular example different from the earlier three examples we've seen. Okay, so now the only difference here is, again, if you sort of pinpoint to what variables you have in the data set. Okay, so of course we have y variable which we want to predict, and in this case it's nothing but BMI, right? So factors affecting BMI. So how do all the other factors, age, gender, exercise, etc., etc., affect the BMI of a person? And now instead of a single x, we have three x's, at least in this example, x1, x2, x3. So my x1 is age, my x2 is gender, and my x3 is nothing but exercise. Alright. So the only difference in this example with respect to all the earlier ones is that we have a single y which we want to predict down the line, but not just a single x, but three of those. Okay. And of course, this is a very standard problem in regression, that let's say if you bring in several variables and not just one, x1, x2, x3, let's say up to some xi, right, where xi is the ith variable, then how do all the x variables affect my y variable? Okay. So a very important point to note here is that when you are sort of constructing a regression model, there should be a single y always. So there should be a single y always, and there could be 1, 2, 3 or more than 3 x's which are nothing but different variables, and the underlying problem to sort of solve is that how do all those x variables affect the y variable. Correct? Okay, so again we will start with some definitions so that you will understand what exactly we have been speaking all this while. So again, examples are on their side, but then again we will try to develop the regression model one by one. Okay. Alright, so again the goal of regression analysis is to model the relationship between independent variables and a single dependent variable. So again I am trying to introduce some terminologies now. So now here you see you have two different varieties of variables. On one hand you have independent variables which are also called as predictors, by the way, and on the other hand you have a dependent variable which is also called as a response, by the way. Okay. So here can you tell me that out of x and y, which one is the independent variable and which one is the dependent variable? So again the answer is the dependent variable is y, so whichever variable you want to predict, okay, and independent variables are nothing but all the other variables using which you are trying to predict the dependent variable. Okay. So again if you go back just a single slide where you had BMI and age, gender, exercise, etc., my response variable or dependent variable is nothing but BMI, which I want to portray down the line or predict down the line, and age, gender, exercise, etc., or any of the other variables form the independent variables, and using the independent variable set I want to predict the dependent variable which is nothing but BMI there. And again, by the way, rather than saying dependent, independent, I mean just a different alternative terminology is to say predictor versus response. Okay. But again the idea about regression model is you have twofold sort of an entity here. So on one hand you have estimation, which is nothing but models the relationship between a predictor and a response with an observed data set. So the first goal of any regression modeling is doing some estimation. Okay, we will exactly see what do you mean by estimation. And once you sort of estimate the regression model, the ultimate goal is nothing but prediction. So predict some new outcomes given a set of inputs with an inbuilt regression model. So again, this built model that you see here is nothing but the regression model that you will sort of form or sort of create. Okay. So again, just to summarize, the idea behind an underlying regression model is twofold. on one hand you have estimation, so estimating all the unknown parameters. On the other hand you have prediction, so predicting some new outcomes given a set of inputs. Now again these inputs are nothing but the predictors, okay, or nothing but the independent variables which we have just defined in the beginning here. And using a set of inputs or the predictors, you want to predict a new outcome, and this new outcome is nothing but the response that you have, okay. So hopefully I have tried to sort of boil down the basics of regression modeling, and again I can summarize very quickly here that the idea is to construct a linear regression model containing the effect or relationship between two variables, or of course more than two variables. On one hand you have a response variable which is a single y variable, and on the other hand you have either a single x variable or several x variables which are called as predictors, okay. And then the idea behind developing the regression model is to sort of create a linear model between all the x's and a single y. Alright, so before we sort of delve deeper into regression model and I will tell you some nuances, some parameters, all of you should be very confident about what you mean by scatter plots, okay. So I am very sure you might have seen them, you might have heard about them, you might have created them sometime before. So a scatter plot is nothing much difficult to understand. So let us say if you have two variables, now here we have a simple example, that speed of cars and distances taken by them to stop, okay. So you have several cars, let us say, and one of the variables would be speed of the car that you see on the x axis in miles per hour, and on the other hand that you see on the y axis is nothing but stopping distance in feet, okay. So depending on how much the speed a car has at any given time point, then the y axis or the y variable measures the distance it takes to completely stop the car. And a scatter plot is what? So scatter plot is nothing but, let us say, depending on how many observations you have in the data set, you simply try to plot them in a 2 by 2 plot. So you have two axes, x axis versus y axis, and then all these points are nothing but different observations you have on the data set. So just to sort of pinpoint to one point here, let us say if you focus on this point on the top right corner, then we can see that the speed of the particular car there is close to 25 mph, while the stopping distance is 120 feet. And again, a natural question to ask is that obviously if you have more speed to the car, then a longer it has to take to stop, isn't it? So hence you can see an upward sloping sort of a line there, okay. So again the idea is that through regression modeling I will try to sort of create an equation of this red line here, and then that equation on the red line would be nothing but the equation of my completely fitted regression model, okay. But again from a scatter plot you can sort of understand the behavior of the data set or the general trend in the data set, etc., and you can draw some very basic conclusions. For example, again just to reiterate that if you increase the speed of the car, it will take all the more distance to stop the car entirely, okay. So if you see here for cars having lower speeds, even lesser than 5 miles per hour, it hardly takes around 10 feet to stop them completely, whereas a car having, let us say, we have seen this, around 25 miles per hour as a speed takes much longer, let us say 120 feet to stop that particular car completely, okay. Alright, now before we understand a statistical relationship or any relationship between x and y which we are trying to model, we have to understand that on the other hand we have a very simple relationship to start with, which are called as deterministic or functional relationships. So what exactly are these relationships? Simple example would be Celsius versus Fahrenheit, okay. So this is a well known equation, so Fahrenheit equals 9 by 5 into Celsius plus 32. And then why is this relationship called as deterministic? Because if you feed in any Celsius value here, then should give it, the equation should yield a particular fixed Fahrenheit value, right. And why exactly? Because these constants here 9 by 5 and 32 are fixed, isn't it? So there won't be any change in these two constants 9 by 5 and 32. So if you sort of have a scatter plot between Celsius and Fahrenheit, you will see that all the points are lying exactly on a straight line, okay. So hence all such relationships defeat our purpose of regression modeling, because there is nothing random here, isn't it? So again, like I said, if you feed in any Celsius value of a temperature, it should give you one particular fixed value of Fahrenheit. So it won't happen that, you know, if you feed in a Celsius value, then the Fahrenheit value might change. This won't happen, right? Because these constants essentially in the equation of a straight line are fixed there, okay. and hence we will call such relationships as deterministic or functional and so on. And again, like I said, the crux of the story is that we are not interested in such relationships when we talk about regression. Okay. Then on the other hand, all the other relationships which are not fixed are called as statistical relationships. So the relationship is not perfect, and here you see the example we've seen earlier in the beginning of the session, particularly related to the location of a person versus the mortality rates, the cancer mortality rates. And here you see that you have a scatter plot, but again all the points, even if you draw a straight line here, all the points are not falling on the line. So there is always some scatter there, there is some trend there. So in general there is some randomness in the points, okay, unlike what we saw in the Celsius versus Fahrenheit case. Okay. So hopefully this small point is clear that whenever there is randomness, there is scatter among the points, there is some trend, we are sort of more interested in sort of developing a regression model for such situations. Okay. Now again, the straight line that you see here is nothing but the ultimate regression line or the regression model. We will try to fix it there. Okay. So now we will start by explaining what do you mean by simple linear regression, or it's also called as SLR. So if you see SLR in your textbooks or somewhere else, it sort of tells you that you have a simple linear regression setting. Okay. Now what do you mean by simple linear regression? So simple linear regression is a statistical method which allows us to summarize and study relationships between two variables. Again, we've discussed what these variables are, but again just to summarize, on one hand we have an explanatory variable also called as predictor, independent variable denoted as X, and on the other hand we have an outcome variable also called as response or dependent variable denoted as Y. Okay. So I will say that all these are alternative terminologies. So either predictor, independent variable or explanatory. On the other hand, either response, dependent variable or outcome variable. Okay. Now SLR, why is it called a simple linear regression? So SLR is called as simple as it relates to the study of a single predictor variable. So again we will start things easy. So we will only assume that you only have a single X and a single Y. Okay. So if you only have a single predictor variable, and then of course the Y variable is always a single variable, we discussed this number of times before, but rather than having number of different X variables, if you only have a single X variable, then the underlying setting is called a simple linear regression model. Alright, so now slowly we will try to sort of get into some notation, some intricacies of a regression line, and then the idea here is called as a best fitting line. So what do you mean by a best fitting line? So again a simple example in front of you. So you have data about heights and weights of 10 different students, and here, so again you have a scatter plot in front of you, and you have a simple question to answer, that which line do you think best summarizes the trend between height and weight. So you have two lines here, one of them is a dashed line, other is a solid line, and if you compare the dashed line with the solid line, which line do you think summarizes the overall scatter plot between heights and weights of 10 students. So again you may pause the video any duration you want and try to answer this simple question, that is it the dashed line which seems to better represent the behavior, or is it the solid line? Okay. Now of course my opinion is that it should be solid line. Of course your answer might be different also, but again just to give you a simple reason is that at least 3 points you see here are falling on the solid line. Okay. So if you compare the dashed line with the solid line, I think personally that the solid line is slightly more closer to all the data points, or is slightly evenly placed among all the data points, right, as compared to the dashed line. Okay. And down the line very soon we will see that we can sort of mathematically prove this idea as well. Okay. Okay, so some notations apart from X and Y before we delve into the actual model. So first, an experimental unit. So nothing difficult here. So an experimental unit is an object or person on which the measurement is made. Okay, it's called as an experimental unit. Now the first notation is Yi. So Yi denotes the observed response for experimental unit I. So far we've been dealing with variable Y, right? Now again let's say in the entire data set you have, so let's say this is the data set X and Y, and how many observations you have? So you have I observations in each. Okay. So then I can simply write down Xi and Yi. So what do you mean by Yi? So Yi is nothing but the observed response for the ith observation. Similarly, Xi is nothing but the observed predictor for the ith observation. And lastly, when you sort of create the regression model, Yi hat denotes the predicted response for the ith observation. So you have three entities here, Xi, Yi and Yi hat. Okay, so Xi and Yi are nothing but the actual data that you have, and once you fit the regression model between Xi and Yi, then down the line of course you want to predict the response. So my yi hat values or this notation denotes the predicted response for experimental unit I. Okay. So from all these notations you should sense one simple thing, that on one hand we have yi, on the other hand you have yi hat. So yi is the actual response, yi hat is the predicted response. So how much error are you making, or how much error is the regression model making? Okay. So this is the crux of capturing the error or finding the accuracy of the regression model, isn't it? Because on one hand you have the actual y that you are observing, on the other hand you have the predicted y which the model is giving you, and of course the assumption should be that these two should be close, right? So how close? Okay. So this is exactly what tells the accuracy of the regression model you've fitted. Okay. Alright, so now we will spend some time on understanding this regression model very briefly. So the assumed population regression model is given by this. So again, like I said, you have to establish a relationship between xi and yi through this equation of a straight line. So yi equals beta naught plus beta 1 xi plus epsilon I. Okay. So again I will try to explain this very briefly, that beta naught and beta 1 are the parameters, okay, which you want to estimate. So parameters in the regression model, xi is the predictor vector, yi is the response vector, and since this is, you are sort of fitting a statistical relationship, there has to be some random error in the model. Okay. So again, just to understand, this is not a deterministic relationship, isn't it? So since you are trying to capture some randomness in the data, there has to be some random error in the model also. So this epsilon I denotes nothing but the random error. Now assuming you fitted the regression model, the line of best fit, okay. Now again the line of best fit is what? So again if you go back to all the examples you've seen, so be it cancer mortality rate or any other regression model, okay, and then let's say heights versus weight example. So in every scatter plot, let's say this is a scatter plot, you've seen a straight line, isn't it? So this straight line is nothing but the line of best fit, and its equation is given by this equation. So yi hat equals b0 plus b1 xi. Okay. So here again just to spend very briefly some time on this. So what exactly do you think is b0? So b0 is nothing but beta naught hat, so estimate of beta naught, and b1 is nothing but beta 1 hat, or the estimate of beta 1. Okay. So lastly I will try to very quickly explain that what's going on behind these two models. So on one hand you have the population regression model which you assume to be true, which is the first equation you see here, and since it is a population regression model, it should contain some unknown parameters, namely beta naught and beta 1. And lastly, since you are trying to capture some randomness in the data, it should also contain some random error. Okay. Now let us say from the observed data you have xi and yi, you try to fit a regression model which is nothing but the straight line that you see in any example, and the straight line is called as line of best fit, and the equation of that line of best fit is nothing but the second equation you see here. And now interestingly, nothing should be unknown here. So b0 is an estimate that you are getting from the data of beta naught, b1 is an estimate you are getting from the data of beta 1, and again the more interesting part here is that if you notice in the second equation there is no error, right, because now once you estimate beta naught and beta 1, there is nothing unknown left in the equation. Okay. So this epsilon I does not appear in the second equation. So just to summarize, the second equation is nothing but the equation which is called as a line of best fit or least squares regression line, and so on and so forth. So subsequently in the next sessions we will delve deeper into the nuances of these parameters, how do you establish a line of best fit, and some assumptions about the regression model, and so on and so forth. Okay. Thank you.